Hello again. In the last video, I talked about Plunike's theorem, which tells you something about how the size of the sum sets of a set, or the iterated sum sets of a set, can grow if you know about how one sum set grows, or one different set. And today I'm going to talk about a different result that also places some constraints on the growth of iterated sum sets, but it's a rather different flavor. This one's going to show, so we take a set A, a finite set A that lives in an abelian group. The most interesting case is when it's the group is Z to the D for some D. And we look at the size of NA as N increases. And we're going to prove a theorem of Khovanskii that says that that growth will eventually agree with some polynomial. So it can start off not as a polynomial, but eventually when it'll settle down, and the size of NA will depend polynomially on N. I'll write that down a little bit more formally. First, sharing my screen. So Khovanskii's theorem says the following. Let me just get my pen a little bit thicker. Khovanskii's theorem. Let A be a finite subset of an abelian group. And let FA of N be the size of NA for each natural number N. Then there exists some natural number NA. Well, there exists NA and a polynomial PA such that FA of N equals PA of N for all N greater than or equal to NA. In other words, the growth of this function FA of N, or the growth function FA, which is the size of NA, agrees with this polynomial here as long as N is sufficiently large. Now, if you know that if you wanted to show that the growth was actually a polynomial, you could imagine there might be an easy proof. But if you've got to show that it's a polynomial from some point on, then that seems a little bit more challenging. And the proof is not that hard to follow. But again, as with the proof of Plunike's theorem, it's not at all obvious. And again, it's just a theorem that repays a bit of thought in advance, so and a bit of an attempt to prove it for yourselves. I haven't got time to talk you through something like that right now, but what I can do is just look at a fairly simple example. So I'm going to look at the example A equals 0, 1, 10, 11. And this will give some sort of flavor of how things work. It's quite a simple example because it lives inside Z, but just complicated enough to be interesting to show that the function won't necessarily be a polynomial, but it will become one eventually. So let's just, what is NA? Well, if you think about it a bit, we see that we certainly get everything from 0 up to N. So for example, 2A would be 0, 1, 2, 10, 11, 12, 20, 21, 22. So NA is going to be everything from 0 up to N, and then everything from 10, because I can add 0 to it, and I can add 1 and so on, up to 10 plus N, Now, if n is large, there'll be some overlap here. I'll come back to that. But it doesn't matter. Technically, this is a perfectly legitimate way of writing the set. And that continues all the way up to 10n. Have I got that right? I can take n copies of 10, or I can substitute 11 for one of them, and then I can substitute 11 for two of those 10s, and that'll take me all the way up to 11n. So there we are. That's as far as we can. Obviously 11n is going to be the biggest element. And how many elements have I got here? So if n is less than 10, then the number of elements we've got is, well, we have n plus 1 here, and then another n plus 1 here. And how many groups of n plus 1 have we got? We've got everything from 0 up to 10. We've got 0, 10, 20, all the way up to 10n. So the number of multiples of 10 that we've got here is n plus 1 as well. So we've got n plus 1 times n plus 1. So that is n plus 1 squared. If n is greater than or equal to 10, then this n overlaps with this 10. So basically we just get everything from 0 all the way up to 11n. So fa of n equals 11n plus 1, because it's from 0 up to 11n. And just a quick note, as a sort of sanity check that our calculations are correct. If n equals 9, we'll also get everything from 0 to 11n. So we should expect these two formulae to agree when n equals 9. Well, what do we get? We get 100 here, and we get 100 here. So they do indeed agree. So what you see here is that it's, when I say it's not a polynomial, it does at least sort of start off like one polynomial, quadratic, and then turn into another polynomial. And that's typical sort of behavior, that somehow the degree of the polynomial is kind of going down as more complicated things kind of merge into each other and simplify. But somehow the proof that we're going to see of this doesn't in any way appear to do justice to those sorts of thoughts. It just does something quite different. So we're going to start with a fairly simple observation. To make that, we'll notice that, so let A be A1 up to AR, where here I'm assuming that this is a sort of sensible way of writing the set, and so the set really does have size R, no two of these are the same. Then NA is the set of all sums of the form sigma AI xi, I equals 1 to R, such that each xi is greater than or equal to 0, and the sum of the xi's equals n. Because to form an element in NA, I have to take n elements of A that do not have to be distinct. And so the number of times I pick AI is xi. So each xi has to be greater than or equal to 0, because that's a number of times. And I'm allowed to pick n elements with multiplicity, and that tells me that sigma xi equals n. So when you see this, it's going to be useful to let, so for each x in, I'm going to write n naught for the natural numbers including 0. If you're American and watching this, you'll say, well, of course they do. I think if you're American or French or something, but anyway, for me, natural numbers do not include 0. So I'm writing n0. So for x belonging to n0 to the r, write sigma x for the sum from 1 to r xi, and alpha x for the sum from 1 to r of ai xi. And at least in one paper, this quantity sigma x is referred to as the rank of xi. I may use that word, I may not. But just sort of the size of xi measured with the L1 norm. And alpha x is the element of NA corresponding to that r-tuple x1 up to xr. Right, a few more definitions. Define a partial order, a sort of curly less than, on, sorry, a total order actually. In fact, I'm not even going to define it, it's an already defined thing. So let's just say it this way. Let this be the lexicographical order on n naught to the r. So what do I mean by that? I mean that x1 up to xr is less than y1 up to yr. If for some I, well, basically the first I where they differ, we have that xi is less than yi. So if there exists an I such that for all j less than or equal to I, xj equals yj, and xi is less than yi. So it's called lexicographical because that's, of course, how you work out alphabetical order. If less than is just alphabetical order on an individual letter. And now we're going to make a slightly unusual definition, but well, the word used for it is slightly unusual. We'll say that x is useless if there exists an x dashed that is less than x in this funny order, that has the same rank or same size, and gives the same quantity when we sum using the elements of A. Now, why do we make this definition? I suppose I'll just quickly say, otherwise x is useful. And NA, the size of NA, or yes, the size of NA is the number of useful x such that sigma x equals n. Now that's a trivial statement, but it's one of those things where you need to sort of see that it's trivial, so to speak. So why is that trivial? It's because NA, just remember, NA is what we had before. It's a set of sigma AI xi such that xi belongs to n naught to the r. I won't write that again. And sigma x equals n. Now, if we want to count NA, we've got to make sure we don't count any of these sums twice. So the idea of talking about useless things is to say, well, let's just count this only when So when we've got some of these things that are equal to each other, for different x's, let's just pick the minimal one in this ordering, and that'll be the useful one, and just count that one and not count the other ones because we've already counted it. Or to think of it another way, we just run through all the x's such that sigma x equals n in lexicographical order, and each time we get a new element, sigma ai xi, we include it, and that corresponds exactly to the situation where x is useful. If we don't get a new element, it means that there was something earlier in the ordering where we did get that sum sigma ai xi, so we don't need to count it again. So that's why we say useless and useful. Useful are the ones where, when we're going through in lexicographical order, we count them, and useless are the ones that we don't count them because we've already counted them. Right. So now we're going to have a lemma. But before we do that, I'm sorry to say that we have to talk about another ordering on n0 to the r. So let less than or equals be the usual partial order on n0 to the r. So that is x is less than or equal to y if for all I, xi is less than or equal to yi. So if every coordinate of x is less than or equal to the corresponding coordinate of y, then we say that x is less than or equal to y. And now comes the lemma. If x is less than or equal to y and x is useless, then y is useless. So uselessness, so to speak, propagates up. Or to think of it another way, if you've got a useless element and you look at the sort of cone above it in that partial order, everything above it is also useless. And the proof is a simple exercise, but I'll do it. So we're assuming that x is useless. So since x is useless, we can find some x dashed that is earlier than x with the same rank and the same value, sigma xi dashed ai or ai xi dashed. And we somehow want to show that we can also find a y dash that comes before y. And there's a very natural candidate for such a y dashed. So we'll let y dashed be y plus x dashed minus x. So whatever we did to get from x to x dashed, we just do that same thing to y. Got to check a couple of things. First of all, let's note this equals y minus x plus x dashed. So y dashed is greater than or equal to 0 because y is greater than or equal to x by hypothesis. That's greater than or equal to 0, and x dashed is another element of n0 to the r. So also by another hypothesis, that's also a non-negative vector. So we needed that. We also need to show that y dashed is less than y, but I think I won't write anything down. I'll just accept this fact that y dash really is less than y, but I'll say why that's the case. So the first coordinate where x dashed and x differ, we have that x dashed of I is less than x of I, and therefore x dashed of I minus xi is negative, and therefore, and that's also the first coordinate where y dashed and y differ, and therefore y dashed is less than y. So y dashed I equals yi plus this negative thing. So that's that really is trivial. And finally, we need to show that sigma y dashed equals sigma y and alpha y dashed equals alpha y, but that's also simple. So sigma y dashed is sigma y plus x dash minus x equals sigma y plus sigma is just a linear map or additive function. And by hypothesis, sigma x dashed equals sigma x. So that's sigma y. And exactly the same proof with sigma replaced by alpha tells us that alpha y dashed equals alpha y. And that's all we needed to do. We've identified some y dash that is earlier than y in lexicographical order that has the same sigma and same alpha. And that shows that y dash is useless. So why did I bother with that? Because that tells us that, so for each x, we can find a minimal, oh sorry, for each useless x, that is, we can find a minimal, and that's minimal with respect to this order, useless x dashed such that x dashed is less than or equal to x. That's a triviality. We just say if x is not already minimal, we can find something smaller. And if that's not already minimal, we can find something smaller. And you can't do that, go on forever. And so we end up with a minimal one. Where was I? Oh, yes. Conversely, if x dashed is a minimal useless element, and x dashed is less than or equal to x, then the lemma tells us that x is useless. So the useless elements are precisely the elements that are at least as big as some minimal useless element. So I'm now going to define a set x. So let x be the set of x dashed in n0 to the r, such that x is, or x dashed is a minimal useless r-tuple, or element of x0 to the r. X is minimal and is minimal useless. Now we have another lemma. Let, I'll give it a new name. Let U be a subset of n0 to the r, then U is standing for useless. Then the number of minimal, actually I won't say number, I prefer to say the set of minimal elements of U is finite. And again, this is something of an exercise. But again, I shall do it. So if U is empty, then there are no minimal elements, and so we're done. So let, and also, I'm also going to say induction on R. That's how I'm going to prove it. So if R equals 1, then U has at most one minimal element. And indeed, if it's non-empty, it's got exactly one minimal element. So we're done. Otherwise, I'm being a bit fussy about assuming it's insisting that it's non-empty, but there we go. If U is non-empty, let U be a minimal element of U. And again, I haven't sort of actually proved there must be one, although I did say something that was basically a proof. So if you've got an element of U and it's not minimal, pass to a smaller one and pass to a smaller one, and it's quite easy to see that you're always decreasing at least one of the coordinates of U. So the size, which is always an integer, is going down. So that process must stop at some point. So let's pick a minimal element of U. So if that's not, so well, so then for every other sorry, so say for every V in U such that U is not less than or equal to V. So these will exist if U is not the unique minimal element of U, in which case obviously we'd be done. So for every V such that U is not most V, there exist some I and some T which is less than Ui, such that Vi equals T. So V has to be smaller than U in some coordinate, and that so if that coordinate is the ith coordinate, Vi has to be between 0 and Ui minus 1. So now I'm going to say let Vi T for I between 1 and R and T between 0 and Ui minus 1 be the set of V and U such that Vi equals T. So I better write this down because it was important for sort of 1 less than or equal to I less than or equal to R and 0 less than or equal to T less than Ui. So there are finitely many of these sets here. But notice also that because every element of VIT has the same ith coordinate, then VIT is isomorphic to, it's order isomorphic to a subset of n0 to the r minus 1. So each VIT is order isomorphic. And the order isomorphism, I'm not pulling the wool over your eyes, you just get rid of the ith coordinate and squash them up. It's order isomorphic to a subset of n0 to the r minus 1. So by induction, it has finitely many minimal elements. And also there are finitely many of them. And we're pretty much done there. The only observation left to make is that every minimal element of U has to belong to some VIT, and it'll have to, if it's minimal in U, it'll certainly be minimal in VIT. So the minimal elements of the VITs include all the minimal elements of U, which this therefore proves that, so let's say, just to finish off, every minimal element of U is either U or a minimal element. Of some VIT. So we're done. So that was a sort of slightly non-trivial remark to make just at the very end there, but not a difficult one. And we're jolly nearly at the end of the proof, actually. But just before we do that, in fact, we're so near that I think I want to tell you what's going to happen. So we now know, so I'll write this down. So we now know that there are only finitely many minimal useless x, or x dashed. I'm using that letter for the useless ones. So let's just imagine that they're living in, everything's living inside z squared, just so I can draw it. So here I've got 3 minimal useless elements. And now let's pick an n so that the set of all x of size at least n is to the right of all these things here. So in other words, the set of x such that sigma x equals n is going to be a line with this slope gradient -1. And I'll move it far enough up so that it's got past all the minimal elements. And if I do that, and then I sort of look at how many, I know that what I'm trying to count is the NA, as we saw before, will be the number of useful elements here. So I want to take all the elements and I want to remove the useless ones. And the useless ones are precisely the ones that lie above in the partial order, one of these minimal useless ones. So I've messed up the drawing. So let me just get rid of those 2 points and redraw them, let's say here and here. So I've got rid of all those ones, and I've got rid of those ones here, and I've got rid of those ones here. Now what we're going to show is that the set of things that I get rid of above each of these minimal elements has a size that depends polynomially in n. And what is the size of the total number of what is the total number of elements we remove? We can work that out. Of course, they overlap, which is slightly annoying, but we have a technique for dealing with those sorts of annoying overlaps, which is called the inclusion-exclusion formula. So we just use the inclusion-exclusion formula. Every term in the inclusion-exclusion formula will be a polynomial. So we've got a huge bunch of polynomials, which we add together and get a polynomial. So that's basically how it's going to go. So now I want to, one other remark, which is that when we do the inclusion-exclusion formula, we have to look at intersections of some of these sets that have been got rid of, but each intersection is just going to be something like that, and another set of elements that are bigger than something or other, and so it still depends polynomially. But we'll see that in just a moment. So I want to prove another lemma, which is let x dash be an element of n0 to the r, and let n be greater than or equal to sigma x dashed. Then, let's have some notation. Let c x dashed n equal the set of all x in n0 to the r, such that sigma x equals n and x dashed is less than or equal to x. So if x dashed is a minimal useless element, c x dashed n is going to be the set of all vectors of size n that we know are useless because they're at least as big as x dashed. Then the size of c of x dashed of n equals n minus sigma x dashed plus r, choose r. And let's prove that. The way I'm going to prove it is I'm going to define various bijections. So given x in Cx dashed n, map it to x minus x dashed. So this is still going to be greater than or equal to 0. This is a bijection from Cx dashed n to C naught n minus sigma x dashed. That's easy to see. So given any given any x in Cx dashed n, then when I subtract x dashed, I will be subtracting sigma x dashed from sigma x. And whereas I previously had something that was at least as big as x dashed, now I've got something that's at least as big as 0. I mean, and to see that it's to invert it, we just add x dashed again. So that's obviously a bijection. So next, given, so I'm also, it's going to be nice just to, so I don't have to keep writing n minus sigma x dashed. Let's let m equal n minus sigma x dashed. And now, the map x1 up to xr goes to x1 plus 1, xr plus 1 is a bijection from C naught m to the set of, let's call it y in n to the r, such that y1 plus yr equals, well, we've added 1 to every coordinate. Previously it added up to m, so now it adds up to m plus r. So that wasn't very complicated. I leave it to you to prove that that's a bijection. And now I want to do one more thing that's very slightly more interesting. There are all sorts of ways of proving this, by the way. They're all essentially the same, but and I do different things in different years when I lecture this, actually. So the map y1 up to yr maps to y1 plus y2, y1 plus y2 plus y3, all the way up to y1 plus yr. Sorry, I didn't want those brackets there. I wanted curly brackets. Is a bijection from the previous set, so the set of y that had that property, to the set of subsets of 1 to m plus r of size r. And that's ever so slightly less obvious. It's a bijection, but first of all, do we get a subset of 1 to m plus r? Well, y1 is at least 1 because these are now positive integers. y1 plus y2 is strictly bigger than y1, so this is a strictly increasing sequence because all the yi's are positive integers, and y1 plus up to yr is, wait a minute, I've made a slight mistake. So that actually equals m plus r. So what I should say here is m plus r minus 1 of size r minus 1, because this element here is forced to equal m plus r, but the one before it is then strictly smaller. I will have to go back and modify the statement in just a moment. It doesn't actually matter too much what the statement is, as long as it depends polynomially, which it does. But obviously we do want to get it correct. And what is the, it is inverted by the map. Well, I suppose what I've just written here is strictly speaking false. It is a bijection to the set of subsets. Perhaps I'll write the true statement. So there is a further bijection that would make that true, but it's actually better to say something. Of size r that contain m plus r. So it is inverted then by the map A1. I've got a set like that. So I'm assuming I've written these things in increasing order. And that's going to map to, so how do I recover y1 up to yr if I'm given these things here? Well, that's easy enough. y1 equals y1, so I have to have a1. And then y2 is this one minus this one. So a2 minus a1. And that goes all the way up to this one minus the last one. So ar minus a r minus 1. And this now should be back to an ordered r-tuple. And from that we conclude, let's go back and, so I'm going to put end of proof symbol, but I want to go back and correct the statement. So that shouldn't have been plus r, it should have been, because the number of sets, subsets of 1 to m plus r that contain m plus r is the same as the number of sets of subsets of 1 to m plus r minus 1 of size r minus 1. So I just put, an m was this, so I put that minus 1, choose r minus 1. Okay. I think the notes that I've written as they currently are contain that mistake, so I will correct that before too very long. So we're now basically done. So let me just say proof of Khovanskii's theorem. So the size of NA is the number of useful x such that sigma x equals n, which equals the size of that is the set of elements of size n that are at least as big as 0. So that's all elements such that sigma x equals n. And I've got to take away the size of the union of, and that's, I hope that I defined x to be a set of minimal elements. Yes, I did. So x over here was a set of minimal useless r-tuples. So I've got to take away all x dashed in x C x dashed n. And so what have I done? I've taken all potentially useful elements and I've removed all the useless ones, because I know that each useless one is going to belong to one of these sets here. So I have to take the union of them. So by the inclusion-exclusion formula, that is minus, or I'm going to write it like this, plus the sum over all subsets y of x of -1 to the size of y times the intersection of all x dashed in y c x dashed n size of. So let's just quickly check that I've not made a daft mistake, although again, it doesn't really matter if I have made a mistake, because all I care about is that it's going to have a polynomial dependence. But first of all, I'll remove all the, I'll sort of subtract the sizes of all the cx dashed n's. So that's where I take y to be a singleton. So I'm subtracting because it's -1 to the 1, and then the intersection is just over a singleton, so it's just the size of cx dashed n. So the first singleton terms look good, so I think the whole thing will be good. And but the intersection over x dashed in y of cx dashed n is c of max x dashed in y x dashed n, where what I mean by that is this is a vector. So perhaps I'll just write a sort of formula. It looks a bit strange, but max x dashed in y x dashed I is the maximum over all x dashed in y of xi dashed. So in other words, each coordinate, I take the maximum coordinate that I've got of all the vectors for that coordinate. If I want to be at least as big as every single x dashed in y, then every coordinate has got to be big, at least as big as the corresponding coordinates of all the x dashes in y. So that's why this is true. And so therefore, so every term in the inclusion-exclusion formula depends polynomially on n once n is at least as big as all these maxima here, but to be at least as big as all of them, it's just enough to be at least as big as the maximum over all x dashed in x of x dashed. So once we get past all the coordinates of all the minimal elements, all the minimal useless elements, sorry, it should at least as big as sigma of that. So the sum of all the coordinates of the maximum of all the minimal useless elements. It's slightly mouthful to say, but the point is that once we get past a certain point, we get polynomial behavior. Now, a rather interesting feature of this proof is that it gives absolutely no clue about when the polynomial behavior starts, which will have to depend on what the set A looks like, but there are certain natural parameters that you can associate with A, such as the cardinality of A. Another one that turns out to be important is the width of A. And if A is a subset of Z to the D, that's defined to be the largest difference of any AI and BI grades. AB belonging to A. And it was actually an open problem to get any bound at all. The place where we sort of lose all moorings and it stops being quantitative is, in fact, that lemma about the number of minimal elements, or the lemma that shows the number of minimal, the set of minimal elements is finite. That's a completely unquantitative step in the proof. And in order to get a quantitative bound, you really have to look in far more detail about what's going on when you take these iterated sum sets. And so it was an open problem until very recently, the last year or so. And the people who did that were Andrew Granville, George Shakan, and Alid Walker, who some of you may have seen lectures of here in Cambridge in part 3. And I can't remember exactly what bound they got, but it was something like, if A is a subset of Z to the D, then we got something like 2 times A times the width of A. This is not necessarily the right bound. I'm just trying to give you a flavor. I'm half remembering it. D plus 4 times the size of A. I'm not quite sure if that's right, but what's that a bound for? That's a bound for this number NA, the number after which you've got the polynomial behavior kicking in. And a thing to note is that we've got sort of exponential dependence on the size of A. And there may be some other D's floating around here. They say in their paper that they believe that the bound they obtained is much bigger than the correct bound. In other words, it should be possible to prove the same result with a considerably smaller bound. So although the rather nice problem of getting any quantitative bound at all for a general set A has now been solved, there is still work to do in a full understanding of Khovanskii's theorem, as well as a number of more precise questions that one could imagine asking. So there's still some interesting research going on in that direction. Okay, thank you very much. And that's it for this lecture, for this video.